The next speaker is Yan Liu from University of Southern California. Yan completed her doctoral work at Carnegie Mellon and then went to work for IBM Research for 3.5 years. And now she's taken up a position at USC. Welcome.
I'll use this mic. Thank you very much. And so today we are going to talk one specific trend of research that I'm working on in my group, which is actually working on uncovering the temporal dependence in multivariate extreme value time series modeling. So before going to the detail, what I'm going to do is draw a big picture for you and then kneel down to the specific questions I'm interested in discussing today. So as we all know, that time series data are essentially everywhere, with astounding amount of time series data available everywhere, such as the climate applications in biology field, on traffic data, social media, astronomy data, and healthcare. We can go on. So there are many interesting research and challenging problems out there for us to discover. And for my particular interest, I'm interested in answering one specific question, which I think is very important task in from data to knowledge discovery perspective, which is actually trying to uncover the temporal dependence between time series data from multi-time series. All right, in order to motivate that, I'm going to give you 3 different types of applications to tell you what specifically we're looking into, and then try hopefully that I can convince you that this is a really interesting and at the same time challenging problem. So the first application I'm going to talk about is the climate change attribution. As we now know, with the development of the satellite equipment, and then we have a lot of different type of sensor data collected on space shuttle or on different machines. And then we are going to get a lot of different time series of data on climate forcing agents. So this will be petabytes or exabytes of data. And then one important question that we are interested in answering is that what could be the potential factors that leading to the climate change that currently undergoing throughout the world. And in particular, given this type of time series data, we're interested in generating a specific graph, which we usually call as the temporal causal graph. And each node will represent a particular climate forcing agent. For example, we are going to have the temperature, the aerosol, or the CH4, and etc. And then for each edges, we're going to represent it from one particular node to the other one. For example, we have an edge from aerosol to temperature. Whenever we have an edge different from the common graphical model, this particular edge actually represents the temporal dependence. It means that whenever there's an edge, for example, aerosol to temperature, it means the current value of aerosol will actually affect the future values of temperature. And this could be very important in 2 perspectives. The first one is that actually this can reveal important insights in terms of what could be the potential temporal dependence structures that we can uncover from this large amount of high-dimensional data. On the other side, this can also help us to build a better forecast model so that in the future we can build a better forecasting model for particular applications. So this is an example in the climate change attribution. The other example we have is on the biology domain. For example, with the development of microarray technology, we are now able to collecting large amount of time series microarray data, where they will measure the gene activity levels of thousands of genes over different time periods. And at the end, we're also interested in output a particular temporal causal graph in this particular application, that is the gene regulatory networks, in which in the graph, each particular node will represent a gene, and then the edges will represent their regulation activities. It means the current activity of this particular gene will affect the future values of the other gene. And similarly, we can go on into the social media analysis, where we have abundant amount of data available online everywhere. And one of the particular interesting problems we're interested in covering is the social influence networks. So the basic idea is that we can observe for different people. For example, we have the good Twitter accounts in machine learning community, and then we can see what are their frequency of words over the time. And in the end, we can generate this particular social influence network, which means that whenever there's an edge from one particular node to the other one, it means that probably what this particular person A is talking about is going to influence or play an impact to what the other person B is going to talk about. So I hope that with this particular 3 applications in climate, in biology, and social media, I was able to convince you that what exactly I'm trying to achieve, that is, I'm trying to uncover the temporal dependence network structures from the high-dimensional time series data. And this is a quite challenging task from different perspectives. The first thing is extremely high dimension, and the second thing is that the temporal structure could be extremely complex, because now we are involving not only the observation from one time step, it could be go multiple steps, it could be go even a large number of lags. So that is why the problem is very interesting, on the other side, extremely challenging. So in my group, we're trying to develop specific solutions for this type of problem. And the particular technique that we're resorting to is what we call as the Granger causality. So Granger causality is a major concept in economics, which also got the which also won the Nobel Prize for this particular concept. The basic idea is quite simple. That is, given multiple time series, or let's say 2 time series, for example, then the basic idea of trying to uncover the temporal dependence, which they call as Granger causality, is as follows. That is, given 2 time series, which is x and y, what we are going to do is we're going to do 2 types of regression. One is that I'm going to do a regression of the current value of x given regressing on its previous histories, and L is the lag, that is the number of histories that we are going to consider. And the second type regression is that I'm not only regressing on its own observations, but also I'm going to consider a history of y. So if I can prove that statistically the second regression is significantly better than the first one, then we can say that actually y will Granger causes x. And this is the basic idea for Granger causality. So for our computer scientists, one of the questions that when we first encounter this particular concept is that how can we scale them? How can we make them more robust and scalable? And this particular work that we have been working on in 2007 is actually trying to merge the 2 development in both economics and machine learning. That is, we have the idea in economics for Granger causality. On the other side, in machine learning area or statistical area, we have the recent development, that is how we can actually use the penalized type of regression to do variable selection or edge selection in graphical models. And that merges to the essential idea. That is, instead of doing the simple significant test, which could not be very robust if we were given limited number of observations but extremely high dimension, what we can do is that instead we can do a penalized regression, where we are still doing a usual regression, but we are going to put a L1 penalty on the regression coefficients. And in this way, we are able to do an automatic variable selection, which in this case turns out to be comparable to the significant test, which we can uncover the temporal dependence. So this is the basic idea or the basic framework for our model. Obviously, in the practical applications, we are going to face a series of challenges. And this is what we have been doing research work on, for example, in non-stationary time series, spatial time series, nonlinear time series, and specifically just this year, we were working on irregular time series, where we are going to have missing data. We can have gappy time series, how we can actually work out that particular application to recover the temporal dependence network. But in this specific talk, I'm actually going to push forward to another new direction that we are very excited about, which is called extreme value time series. Next, I'm going to do is that I'm going to zoom into the detail for my talk. That is, I'm going to first give you the motivation why we're interested in this particular type of time series, which is called extreme value time series. And then I'm going to talk about my research proposed work and some alternative approach and show you some good analysis results. Okay, so the motivation is quite clear when we work on with the climate scientists. So one of the basic ideas in climate change is that it's not like, okay, when we observe the temperature, we are going to see the temperature will increase over the time, and that's what we call climate change. Instead, what we observe is actually we are going to observe more frequent occurrences of extreme weather patterns. For example, we are going to experience extreme heat wave. We are going to experience extreme drought. And this is the particular patterns that we are looking into. That is why that we are interested in the extreme value time series. And similarly, when we work on social media, we actually face similar situation. That is, we are interested in predicting what could be the next buzz in the future. And obviously, those buzz won't say, okay, I increase over the time and now you predict me, which is a nice time series modeling problem. On the other side, what happens is that we are going to have a big jump, and that is what we call as extremely high value of what frequencies. And that is the specific question that we are interested in. That is, given the particular extreme high frequency, how can we recover the temporal dependence and also making better prediction models? Here, I give the example, which is really interesting. That is, I have tried Google Trend last night, where we have machine learning, and this is the number of mentions. And interestingly, that has been relatively stable, but on this particular side, we see a little bit big jump. On the other side, what we can see is the big data, that is the theme of this particular workshop. And you can see that recently we experienced extremely high jump. And there could be some interesting correlations or temporal dependence between machine learning and versus the big data theme. And the question is, how can we actually uncover this from multiple number of themes, let's say thousands of themes on the net? Okay, so formulate the problem. Essentially, that specific problem that we are interested in is that given the multiple extreme value time series and how we can recover the temporal dependence from them. And there are different types of extreme value definitions. In statistics, usually there are two of them. One is called block maximum. That is, given a specific time block, we are going to take the maximum value. And the other is that what is called as peak over threshold. That is, we are going to set a particular threshold, and then we can observe any particular value above this particular threshold. And in this particular talk, I'm only going to focus on the block maximum. And the question is, what is the challenges? Why don't you just go ahead using whatever you already there? And the challenge is as follows. The first challenge, essentially, that is they have the heavy tail of the data. So when we observe the extreme values, it's never going to be a nicely fit Gaussian distribution or exponential distribution. Otherwise, we can solve them easily. What we will see is usually the distribution will extremely heavy tail. It means that this cannot be modeled by the common distribution that we are familiar with. And the second problem is the scarcity of the data. That is, it's very unlikely that we observe abundance of them. Most often than not, we just see 1 or 2 or 3 points, and then we're trying to generalize over them. So that is why that this is extremely challenging. On the other side, a quite important problem to solve. And the particular solution that we are going to resort to is what is well known in statistics, which is called the extreme value theorem. The basic idea is very similar to the central limit theorem. That is, if we were given a series of observations x1 to xn, then we can say that the particular sequence of observations will follow a particular distribution, which has the particular form as follows. And this particular family is called the generalized extreme value distribution family. And usually at 3 parameters, mu, sigma, and c. And mu is essentially will control the mode of the distribution. And sigma will control is proportional to the variance, while c will usually depending on the particular behavior of the tail. And this actually similar as exponential distribution. This one covers a big family of distributions. In this particular work, I'm also to zoom in a little bit to actually working on one specific distribution in this family, which is called the Gumbel distribution. And this is a particular distribution when c close to 0. And this is the basic shape for the Gumbel distribution. Now it only has 2 parameters. One is mu and the other is sigma. Mu is controlling the mode of the distribution, and sigma will be controlling the variance. And as we can see, they have extremely heavier tail than the Gumbel, than the commonly known as Gaussian distributions. And in particular, we choose this distribution also because if the particular observations is exponential family, then their extreme value observations will follow the Gumbel distribution. And that is our motivation why we choose the Gumbel distribution. And now we are going to zoom a little bit into the detail, but I'm not going to go over the full details. So the basic idea is as follows. That is, given the observations of extreme values, that is xit, and then we have the particular the value of the mu, which we can define the joint probability distribution of x, and mu, which is the hidden variable, as a product of two things. One is the probability of x given the parameters. Essentially, this can be modeled by a Gumbel distribution. And the second part, essentially, is the probability of the current value of mu given its histories, and where we are going to model something with something that we are very familiar, and that is the Granger causalities. So the basic idea is as follows: that we are going to work with the linear model. That's we define the value of mu ti as a linear combination of the histories of not only the history of the current time series, but also the history of all the time series, so that we can recover the temporal dependence. And also we have Ci, which is a particular location-specific constant, and epsilon t will be the Gaussian noise. And when we observe the data, what we are going to do is that we are going to do a maximum likelihood estimation for the observations, and plus we are going to put a penalization term like what we did for Granger causality. That is, we are going to put a L1 penalization over the parameters, that is beta in here, so that we can achieve a sparse solution, which will lead to a sparse temporal dependence graph. I'm not going to details for the EM algorithm, but essentially we can solve them using the E step and M step. And for forecasting, we can similarly utilizing what is already in the extreme value time series predictions, and the specific prediction can be written as follows. All right, so I'm going to talk a little bit about the alternative approaches before you ask me the question, why not try the others? There are two alternative approaches that currently in machine learning. One is what is called as transfer entropy. And this is the basic idea, similar as information gain, except that we are going to use them for time series data. Essentially, this is trying to compare the differences between two entropies. One is the entropy of Y given of its own history, and the other is the entropy, not only his history, but also the history of X. And if this is significantly big, it means that X will causes or X is related to Y. And in this way, we can actually uncover the temporal dependence. This is a general concept because this does not rely on the specific distributions, and they don't rely on the Gaussian distribution assumption. That is why it's also applicable in this case. On the other side, another popular approach in machine learning recently is the Gaussian copula approach, which is also called as the semi-parametric approach proposed by Yan Liu and John Lafferty. And the basic idea is that instead of working on the specific margin, the probability distribution, they are going to work with the marginal distribution and then convert it into a nicely formed Gaussian distribution, where they can actually utilize the nice theory of consistency proof in the original Gaussian distributions. And this also doesn't rely on the specific distributions of the original data. It doesn't rely on the assumptions of the Gaussian distributions. And that is why this also can be applied. And next, what I'm going to show you is a set of interesting experiment results to convince you that our proposed approach is better than the proposed alternative ones. All right, so the first one I'm going to show is really simple, that is synthetic results. And here we have a 9 time series, and we will generate the extreme values based on their appropriate distributions. And on the graph on the left is the ground truth, that is the temporal dependence network from the ground truth. And the rest of the ones are what have been we talked about, including the simple Granger causality has to rely on the Gaussian assumption. And then we have the transfer entropy, copula, and our proposed model, which is the Sparse-GEV. From this particular results that we can see, that our particular model, that Sparse-GEV, was able to uncover better than the alternative approach to compare with the ground truth. And another set of experiment results we are going to show is on climate data and also on the Twitter data set. So on the climate data, that what we did is that we work with the climatologists, and they have the specific wind and wind gust data. And for the time of limit time, I'm going to only show the results on the New York regions, where we have uncovered the specific temporal dependence networks for how the wind will influence each other. And each particular node in here will represent a particular station, and the edges will mean that this particular edge will have an influence or impact on the future values of this station. And as we can see, in general, there are two types of clusters. One is on the top, and the other is on the lower level. So essentially, on the top level, this will represent the wind influence activities among the inland region. And for this, for the second cluster, this really represent their activities for wind and wind gusts through the coastal regions. So we work with the climatologists and prove that this seems to be agreeing with a lot of the motivations in terms of the terrain and also the geolocation properties for the specific location. And the second results we are going to show is our Twitter data set. Essentially, we're interested in predicting the bus and also what will be the particular temporal dependence between the bus. Here we show two types of results. One is on the specific time frame, that is at the end of 2009, we have a major big breaks, hot topics happening on Twitter website, which is essentially the Haiti earthquake. And that is one of the biggest topic among most of the time during that framework, during that particular time frame. And let's see what are the activities or what are the influential activities for this particular time. So now we just draw a very small subset of the graph of what we learned. Here we have all the hot topics around that time. If you remember Tiger Woods really bad scandal and stuff like that. And then whenever this Haiti earthquake happens, we can see that actually Haiti earthquake will impact all the topics that they have been talking as other hot topics. It means that essentially the whole Twitter website has been taken by the particular buzz or hot discussions on the Haiti earthquake. And similarly, what we did for the Occupy Wall Street, where we have collected data in last October, when the Occupy Wall Street is really at the beginning stage. We want to see what is the activity around that time. So we collect a different hashtag and there are different type of mentions. So this is the resulting learned temporal causal graph, temporal dependence network. So this is the central theme, that is the Occupy Wall Street. On the other side, we have Occupy LA, Occupy San Francisco, and Occupy DC. From this graph, this is trying to tell us that essentially for the single linkage, that is for LA, DC, or San Francisco, they all impact or being impacted by the Occupy Wall Street, but they don't impact each other for San Francisco versus DC. So this is some interesting results of the graph that we learned. On the other side, we also want to verify by prediction results. And this number is shown by the specific relatively root mean squared error. And across all the different disciplines, our method is able to achieve a better prediction results for all the challenging tasks that we talked about. So I think I'm running short of time, but I just want to glance over a little bit. Since we're talking about complex models, but on the other side, we're interested in applying this to a large number of high-dimensional data. So the question is, how can we make them scalable? One of the initial efforts that we tried is actually doing the parallel stochastic optimization algorithm. We tried different type of algorithms that has been talked about in the literature and given interesting results. So from what our observation is that essentially this particular algorithm, which is the parallel stochastic gradient descent algorithm, seems to provide the best results in terms of both saving the iteration time and also their convergence time. All right, so with this only limited 20 minutes, I hope that I was able to convince the story to you in terms of what I'm interested and passionate about. Essentially, we are interested in uncovering the temporal dependence relationship from the high-dimensional time series data. And hopefully that this can open up some new directions and interesting discussions for the rest of the workshop. Thank you very much.
Thank you. we only have time for, I'm afraid, one very short question. I'm sure there are many. Does anyone have a brief question they'd like to talk on my setting up?
How do you cross-validate some of these parameters, like the capital L, if you don't have essentially any training data? So if you don't actually know what the answer is, because that sort of extreme event hasn't happened.
So we're asking about the cross-validation for L, that is the lag time. Yes, so this is essentially another research directions. There are many different research efforts have been pushing forward, but the basic idea is that we can either do simple cross-validation. On the other side, we can try bootstrap. And there's no universal particular correct answer yet, and that is also one of our own research efforts. I don't have very good solution right now for you, unfortunately, but I think what you point out is a very challenging problem from practical perspective. Yeah.
Thanks
Thank
very
you.
much. The next speaker is Yan Liu from University of Southern California. Yan completed her doctoral work at Carnegie Mellon and then went to work for IBM Research for 3.5 years. And now she's taken up a position at USC. Welcome.
I'll use this mic. Thank you very much. And so today we are going to talk one specific trend of research that I'm working on in my group, which is actually working on uncovering the temporal dependence in multivariate extreme value time series modeling. So before going to the detail, what I'm going to do is draw a big picture for you and then kneel down to the specific questions I'm interested in discussing today. So as we all know that time series data are essentially everywhere with astounding amount of future where we can build a better forecasting model for particular applications. So this is an example in the climate change attribution. The other example we have is on the biology domain. For example, with the development of microarray technology, we are now able to collecting large amount of time series microarray data, where they will measure the gene activity levels of thousands of genes over different time periods. And at the end, we're also interested in output a particular temporal causal graph in this particular application, that is the gene regulatory networks, in which in the graph, each particular node will represent a gene, and then the edges will represent their regulation activities. It means the current activity of this particular gene will affect the future values of the other gene. And similar I'm going to talk about is the climate change attribution. As we now know, with the development of the satellite equipment, and then we have a lot of different type of sensor data collected on space shuttle or on different machines. And then we are going to get a lot of different time series of data on climate forcing agents. So this will be petabytes or exabytes of data. And then one important question that we are interested in answering is that what could be the potential factors that leading to the climate change that currently undergoing throughout the world. And in particular, given this type of time series data, we're interested in generating a specific graph, which we usually call as the temporal causal graph. And each node will represent a particular climate forcing agent. For example, we are going to have the temperature time series data available everywhere, such as the climate applications in biology field, on traffic data, social media, astronomy data, and healthcare. We can go on. So there are many interesting research and challenging problems out there for us to discover. And for my particular interest, I'm interested in answering one specific question, which I think is very important task in from data to knowledge discovery perspective, which is actually trying to uncover the temporal dependence between time series data from multi-time series. All right, in order to motivate that, I'm going to give you 3 different type of applications to tell you what specifically we're looking into, and then try hopefully that I can convince you that this is a really interesting and at the same time challenging problem. So the first application, the aerosol or the CH4 and etc. And then for each edges, we're going to represent it from one particular node to the other one. For example, we have an edge from aerosol to temperature. Whenever we have an edge different from the common graphical model, this particular edge actually represents temporal dependence. It means that whenever there's an edge, for example, aerosol to temperature, it means the current value of aerosol will actually affect the future values of temperature. And this could be very important in two perspectives. The first one is that actually this can reveal important insights in terms of what could be the potential temporal dependent structures that we can uncover from this large amount of high-dimensional data. On the other side, this can also help us to build a better forecast model so that in the